so you have a separator. So after separator, actually you have a RI beam of around energy around 1.7 kV per nucleon. Then we have many accelerators because this energy is useful only for material science studies, not for nuclear physics. So you accelerate in steps. Our RF cube is 99 kV per nucleon. At the end of third linear, 415 kV per nucleon. Then 1 MeV per nucleon, 2 MeV per nucleon. The color code corresponds to what is the operating frequency of each RF accelerators. Around 400 kV per nucleon, we have a charge stripping stage where we increase the charge state from 1/14 to 1/7. This is the three-dimensional figure of the whole layout. You can see this is the cyclotron beam. And then this is the ion source, RF cube, rebuncher. These are the different linears. Finally, superconducting water resonators. So first, let us start with the R&D of targets. So first of all, the target should be thick, or it should be multiple thin targets, because we have to maximize the production cross-section of RI beam. So we are at present concentrating on multiple thin target approach. The thickness of each target should be such that the ripples can come out. Number of targets will depend on the width of the reaction channel energy window, and the targets can withstand beam irradiation for days together. For thin target, that is an advantage, but for thick targets, where the entire beam is almost stopped within the target, this thermal management of the target is an issue. And then by using multiple thin target, after that we collect all the reaction products from multiple targets using gas jet liquid transport and feed it to an ion source. And the advantage is the fast and efficient and element independent process. And the issue we have to handle here is taking care of huge gas load of the support gas, because no ion source can work with such a huge gas load. So something has to be done. This is a picture of the target chamber we have been using for many years now, and many interesting results have been obtained. I'll show some of them. The next part I'm trying to cover is the online ion sources. Here we need high charge states, but in RIB the problem is you cannot really get high charge state because the ion source is very close to the target where the vacuum is poor. So generally you use cascade of ion sources. So here I will show you a few of examples of that. So this is one ion source which has been built just in 2002 million last year. This is one of the oldest ion sources that was built in 2002. And then we are having operation built around 1988, this type of another ion source. And three of them are here, and the fourth one is the surface ion evolution hollow cutoff type of ion source. So we have been working on all these ion sources for many years now. The next part I'm going to touch upon is the isotope separator that basically separates or single out the RIB which you want to accelerate thereafter. I don't have any further slide on that. This is a simple combination of magnets and beam optics. Then the first acceleration is done by RFQ, because this is the ideal accelerator for very low energy ion beams. We built actually two of them. The first one was commissioned in 2005 and the second one is 2008. This is the one which is being used regularly now. And incidentally, historically, this is the very important one because this is India's first RFQ. Next, I'll go linear accelerators. You can show there are 5 linear accelerators shown by these brown arrows. We have many. We have already. This is a typical picture of one of them from inside view, the outside view. First, second, third has been already commissioned in 9, 10, and 11, 12. Beam acceleration has taken place. The fourth and fifth has been installed in the line. The beam acceleration has not been done yet. Then, for proper longitudinal focusing during the acceleration process, you need rebuncher cavities. Rebuncher cavities are nothing but very small accelerators which does not produce any acceleration. It just compresses the beam in the longitudinal direction. We have made 5 of them. This is a typical picture of one of the rebunchers, and these are the commissioning or your installation district. And finally, I'll show you the superconducting quarter-wave resonator QWR. This is shown here because what happens by using room temperature accelerator, you can achieve some energy, but then the power consumption is very high. So after some time, you go for superconducting technology. So we are going into that direction also. So there will be 2 cryostats. Each cryostat will contain 4 quarter-wave resonators and 1 superconducting solenoid. So this is a picture of that. This is a picture of 1 quarter-wave resonator. There are 2 acceleration gaps, and this is a typical picture. This is actually the result of last year. This project we are doing in collaboration with TRAN. All quarter-wave resonators have exceeded their operating gradient of 5.5 million volt per meter. In fact, you can see this one we can operate safely up to 6 MV per meter, maybe even beyond that. So now I will just take a walk around the facility, starting from RFQ, Revancher. This is a view from the other side, you can see. Then you can see the Revancher 3, Linac 3 here, Linac 3, Revancher 4. It is the same view from the other side of the cave. And this is the dipole magnet, Linac 4, and Linac 5. Then using this facility, we have accelerated nitrogen 4 plus beam up to the end of Linac 3, up to this point. Because beyond that, we don't have the radiation permission from AERB till today. So we have done, this is just preliminary results. So up to 415.3 kV per nucleon we have accelerated. Don't concentrate too much on these current values. All these accelerators are designed for more than 95% transmission, and that will be achieved. And this is a picture of a beam spot. Then during this period, over the past few months, we have produced and accelerated some of the RIBs to demonstrate the commissioning of low energy facility. These are the radioisotopes, carbon-11, oxygen-14, etc., and their half-lives. And this is the particles per second available right now. Any RIB accelerator is also a very good accelerator for stable isotope beams, so we can make these stable isotopes are also available. Typical beam currents here can be very high. So stable beams of large number of elements up to 1 MeV per nucleon is available. We will be able to provide all lower energies also. It is a continuously variable accelerators. Rare elements up to 1 MeV per nucleon for a few cases. The list will grow as and when we can increase the intensity in the production stage. Actually, for each and every target, there is a lot of target R&D and ion source R&D involved. So we go through that month after month. And sorry, I didn't want to do that first. Yeah. So with this facility, some experiments are being already done. So these are some snapshots from some papers. Nuclear spectroscopy study with RIB of 43 potassium. Study of the mass distribution of 236 uranium. Argon beam is accelerated in RFQ polycrystalline titanium oxide. And then nano patterning by ion implantation. So some of my colleagues are doing these experiments. As a natural extension of this thing, we came up with the idea of a large-scale RIB facility. Because with our present room temperature cyclotron, we really cannot go to produce many radioisotopes. We have very high intensity. You need very dedicated accelerators for that. So that plan is shown here. So you will have, this is the acronym of the project, ONURID. The highlights of this project are electron linear for production of neutron-rich RIBs. So you can see superconducting electron linear hitting the internal target, and it is produced in RIBs. Proton driver to produce proton-rich RIBs. This is shown in this line. Both isotope and projected fragmentation separator type of RIB facility. As I said, that any RIB facility can accelerate stable isotope beams also, so it will be possible to accelerate both RIB and stable isotope beams of high current. Fragmentation of RIBs for producing near triplet nuclei at the very last stage. So after linear, we plan to accelerate up to 100 MeV per nucleon using a ring cyclotron and projected fragment separator facility. So the question is how equipped we are for planning such a large-scale facility. During my presentation slides so far, I have been showing you what are our expertise, what we have already developed. So for this annual facility, many of those things have to be duplicated. But we can do it because all the RIB accelerators you saw, we have designed them, developed them here starting from scratch. We have the know-how. We are confident we can do it. Now, still, Is life so simple? No. These are the gray areas for this project on which we don't have the technology fully proven today. So we started concentrating on these areas. So the first area is superconducting electron liner, and the second area is target related to the superconducting electron liner, that is a photo-fission target. These are very two crucial areas on which a lot of effort has to be made. And then towards the end of the project, we have the ring cyclotron and we have the projected fragmentation separator, on which also we don't have any expertise today. So these two, we are taking it to the next generation to some extent, and also we hope by the time we reach here, we'll be experienced enough to take up this challenge. But I'm going to show in the next few slides what we are doing here on these gray areas. So I'd like to convince you those areas are not gray any further. Just before that, this is the Rajarat campus master plan where this already facility will come up. Some of the buildings of other facilities have already come up. And these are the layout of the different accelerator halls of the block diagram of the already facility I showed. So we are now working on all the building design, all the regulatory permissions, so on and so forth. So for the electron liner, we had a collaboration with Trant. 5 plus 5 or just 5? Okay. So we have a superconducting electron liner, we need it. So the idea of producing using photo-fission route is you need 50 MeV 2 milliampere electron liner. So that will be done using 5 such 9-cell superconducting cavities. Tram Vancouver had the similar requirement, so we joined hands together and we have already developed one such 9-cell cavity. Some pictures, this is the development of the single cell cavity, this is the development of 9-cell cavity. When this 9-cell cavity goes into the cryostat, this is the cryostat, you can see the Indian flag, and beam has successfully accelerated to 10 MeV using one 9-cell cavity. This is a picture of the beam, and the acceleration gradient is 10 MV per meter. So we have designed and developed this thing together with TRAM, and we have the know-how for these also. So now we have to develop 4 more on which my colleagues are working. But what I was trying to tell, the electron liner area is not so gray now. It is, you can say, we are almost confident we'll be able to pick it up, make it. Then at the beginning of the electron, so this is what has been done in collaboration with TRAM. But then you need the electron gun, the matching beam line, etc., the analyzing section. So this development is going on in our RIB lab here. So you can see this is a picture of electron gun, this is the beam spot, this is the low energy beam transport line. So a lot of developments are actually going on. I cannot, as you can see, I am trying to give the flavor of everything, so I cannot go to the detail of everything. Then this is the second gray area I mentioned, the target technology. Here the case is very high current, electron beam is hitting on the target, and that will be producing a lot of radioactivity. So handling that activity is not straightforward. You have to take help of the robots, it's a remote control, everything. And then it has to be foolproof, it should not fail during operation, and all the connections, controls, you cannot keep close to the beam line. Everything has to come out of the shielding, thick shielding. So these are basically things what you are seeing, those shieldings, and the actual components are below this. You can see the primary beam, this is the target vessel, this is the pre-separator magnet which will be used for separation, and the different components, these are the, so this development is also going jointly with TRAM. We are there also doing the same thing, so we are joining hands together and we are working. This slide is courtesy TRAM. Then, during this journey, there are some memorable moments. Allow me to share a few of them. So this is one in which Professor Vikas Sinha signing an MOU with Nigel Lockyer, the then TRAM director. And by this MOU, actually, this electron liner has been developed, the target R&D is going on. Then, even before that, there was very interesting development with RIKEN in Japan. There is another collaboration with Samir Mumbai in the field of RF transmitters. CMRI Durgapur for the fabrication of RFQ heads. This is another historic picture on electrolinear and target model review meeting. You can see Nigel Lockyer here, DM Arbinga, and our session chairman also visible here, Dr. Bhandari. So actually these are memorable moments. So when you see at the end of the day, it is very satisfying. And I think, yeah, Dr. Alam Chakraborty, he's also our director, and he's actually the person who has made myself, Dr. Vishali Nayak, and the entire RIB group to work in this interesting field of RIB research. I don't have a concluding slide because I have nothing to conclude. We are just beginning our journey. So I can just summarize what I have said so far. So these are the summary. Low energy RIB facility with linear accelerators up to 180 per nucleon is built at VCC. Full-fledged RIB facility called ONURIB is planned at VCC's new campus at Rajarhat, Kolkata. Pre-project activity ONURIB is ongoing. Work on gap areas of R&D, superconducting Linux and high-power active and target technology development is also underway. So with that, I finish my presentation. Thank you very much for your time.
Thank you very much, Dr. Arup Bandyopadhyay, for a very interesting talk. Very complex systems developed. Congratulations for that. So we can have questions, comments.
Very nice presentation on rear and beam facility at VCC, sir.
I'm trying to see her.
Yes, sir. I am. This is, sir, one thing. There is MC50, this medical accelerator is also there for medical isotopes, I think, production. So it is also an additional facility for this type of making isotopes, RIB facility.
No, see, you are talking about probably yesterday Dr. Shom's talk, what you listened. So there is a medical cyclotron facility at Chowkoria. Also, we are developing another, that is being developed, MC18, another proton cyclotron project. Those are the projects for accelerating protons to the energy typically from 15 to 30 MeV, which is required for the production of radioisotopes which are used for clinical diagnosis of cancer cells. That has nothing to do with exotic nuclear research. So here the accelerators I'm talking about are much more versatile accelerators which will be able to give you many different beams to many other energies, and these are typically made for academic research mostly. But that is a commercial machine totally devoted to radioisotope production.
You mentioned in your talk about radionuclide production for medical applications.
Yeah.
The radioactive
So that is
asking the difference.
No, true. So this machine can be also used for that, for the radioisotope production. But this is not the only target of this machine.
This RIB facility has lot of flexibility. Means
Yes.
it can make medical isotopes also and
True.
other R beams also for other
But
research.
shall I tell you something? When you do something for commercial, for example, the MCF facility, what you are talking about, that we deliver to the Calcutta hospitals every day, even during COVID, whether rain or sun. So that is a totally dedicated facility. Here probably what will be possible will be concentrating more on research on new radioisotopes, development of new radioisotopes, and once that technology is established, it will be transferred to a dedicated accelerators.
Thank you.
Yeah.
Hello sir, the question is very basic actually. So we are discussing among friends. That when you talk about heavy ion collision or anything, so why do you always heavy ion collision or heavy fish target heavy ion collision anything? So why do you always talk about the beam energy as per nucleon? Is it because the momentum is QBR and per Q you measure the energy or something else?
You just calculate the velocity from that, and you just calculate the ion's velocity and see what comes into that expression.
Okay, but
So then your answer will be clear.
non-relativistically.
No, relativistically also. So if I tell you energy in MeV per nuclear, you can straight away calculate. You do not need any other information. You can just straight away calculate the velocity. No, so that's not telling you. You need not to mention what nucleus or what. So you just say energy per nuclear, and from that the gamma factor, beta factor comes directly. Beta or gamma, that expression, relativistic expression, you see that there this energy per nucleon comes directly. I need not to mention whether it is oxygen or nitrogen or anything. You can straight away go ahead.
Yeah. More questions, comments? Well, if not, let's thank Dr. Badrupadhyay once
Thank you.
again. We now invite Dr. Chandana Bhattacharya, VECC.